Gentlemen, good morning. This session is on real-time measurement. It's a great pleasure to have you here. My name is Vincenzo Fiori, and I'm chairing this session. We have only 4 papers, so if you like then to discuss more about the topics of the session, we have plenty of time. The first paper is correlation-based detection and localization of RC electronic devices using array detectors. This is a research performed at the Missouri University of Science and Technology here in the US, and is a research carried out by Vivek Thotla, Maciej Zawodorsky, Saranpan Yaganathan, and Sanjay Agarwal. It will be presented by Vivek Thotla. Please.
Good morning all. Thank you for being in the session today. My topic for today is going to be the correlation-based detection of RC electronic devices using array detectors for military applications. Well, the main objective is to detect RC-type electronic devices from their unintended emissions. Now, what do we mean by unintended emissions? Unintended emissions are the characteristics of electronic devices, the emissions that come from the device without their intention, like unintentionally. So our main objective is to identify the devices, detect them, localize them based on their unintended emissions, and also detect multiple of those devices, and then differentiate between the line of sight and non-line of sight to make sure that you're not doing a false detection. So the unintended emissions are basically the radiations from the device that emit unintentionally. The major challenge with the unintended emissions, they are low power, and the signal characteristics, the basic signal characteristics of the signal are unknown, and the range of detection is decreased because of the low power. So we have to come up with other methods than the regular received signal strength methods to detect these devices. So the traditional methods basically use the received signal strength method for detection as the basis for detection. The other detection methods also probably use like tagging methods, where you have a code on the device and you send a signal to get the tag back or the code back to say that this is the device there. And also, another major problem was pre-profiling of the device. You had to know what the actual characteristics of the signal and the device were to detect the device as such. So we want to eliminate all these blocks for better detection and identification of the devices. In the block diagram, so what we have is a basic RF time signal, and there are different methods that have been performed. In one of my first papers, I've actually used a second-order self-similarity method to come up with a parameter called Hurst parameter as a basis for the detection. The received signal strength the received signal strength actually fails when the power goes down the noise floor, so it decreases the range of detection. But if you have a parameter that's more towards the signature of the signal as such, you can increase the range of detection even though the power goes below the noise floor. So that is where we introduced the Hurst parameter as a detection parameter for the RC devices. But then we thought, we're not just looking at one device. What if we have like multiple devices? What do you do? So we came up with an idea of having an array antenna for detecting multiple devices, because if you have an array antenna, if you have multiple devices at different angles, you can get the angle information. So we can use a combination of Hurst parameter and the array antenna for detection. Again, we have another problem now. So what if there's a device and there are reflectors everywhere? So what happens if the line of sight signal is like having lower power, or is it weaker than the reflection as such? So you're getting a false detection. So our main aim here in this paper is to overcome that false alarm of non-line of sight signals over the line of sight signals. So basically, in our experiments, the real-time experiments we have conducted, we have considered a super heterodyne receiver, more like a off-the-shelf walkie-talkie. So we are looking at frequencies at the GMRS and FRS range, It's usually low cost, off the shelf available, relatively larger bandwidth, so it can work over a larger bandwidth. And it employs a crystal oscillator inside for its operation. So that defines what kind of a signal we're going to get out of the unintended emissions, what frequency and everything. Yeah, so as I've told you, the reason why we have come to an array antenna is to make sure that we are able to detect multiple devices at the same time and localize them. So we have actually built a mobile array antenna in the lab itself, because previously when we looked at some of the array antennas, the usual array antennas that are used for detection, they were large. You need a lot of equipment to move them around, but we have built one in our lab itself. So this is the array antenna that we use for the measurements and everything. So basically what we're going to do is we're going to consider the 4-element array antenna that they have just shown, and then for the real-time measurement of the time series data, we're going to do a phased array processing. A general phased array processing is to get the signal, and a coherent addition would give us a phased array processing, and then this is going to give us the basic angle of arrival information based on the received signal strength. But what we want to do is a normalized error correlation function to eliminate the false alarm due to a higher power in the non-line of sight signal. So the basic methodology shows the receiver oscilloscope, where we're going to have the data collected. This is connected to another base station. And then we have 20 dB low noise amplifiers connected to all the 4 antennas. And they're separated by lambda by 2. The basic phased array processing, so this is just going to take the time domain signal, and then we're going to add the phase difference that is due to the distance between the array antennas to have a coherent summation of all the time signals. So yeah, so the theta, the function st theta will give you the time correlation signal with respect to the angle of arrival. So if you're scanning from 0 to 180 degrees, so you'll get the time series signal that is a coherent summation of all the 4-element array antennas. And the basic processing of how to get the power and the angle of arrival with respect to the received signal strength. The challenges in detection of multiple devices. Usually there are cases where the line of sight signal may not be as strong enough for us to be detected by the received signal strength. And this might be due to multipath or reflections, or you could probably have different devices that are uncorrelated. So let's look at the basic scenario. So you just have the 4-element array antenna, you probably have like 2 different sources that are uncorrelated. And then you have like a big reflector that's causing all the problems with the high power with the non-line of sight signal. So when you look at the line of sight and the non-line of sight scenarios, what happens when the non-line of sight signal travels a longer path? So if you consider the timestamp, the line of sight signal is supposed to reach the receiver faster than the non-line of sight signal, because line of sight signal is defined as a signal that comes directly to the receiver. And the non-line of sight is going to take multiple paths. It's going to reflect somewhere, it's going to have a fading effect and everything, but come to the receiver a little late than the line of sight signal. So we will probably try to use that in the time series correlation to differentiate between line of sight and the non-line of sight signal. So we are saying that the non-line of sight signal has a higher correlation with the line of sight signal itself compared to the other sources. So in the case where we have like 2 different devices that are uncorrelated, so when you do a time series correlation between the signal from the 2 devices and the signal from the device and its reflection as such, the cross-correlation coefficient is supposed to be higher for the signal and the reflection compared to the cross-correlation between the signal from one device and the other device. So we're going to use that to differentiate between 2 uncorrelated devices and a long line of sight and non-line of sight signal. And I'm just going to show the basic math behind cross-correlation. So we're just going to have the two time domain signals. We're going to take a cross correlation with respect to the angle of arrival that we are considering and all the angles the array is going to scan. So we're going to take a cross correlation of all the angles, and then we're going to normalize the correlation that we have obtained with the actual theta we are measuring, the angle of arrival for each of the angles, for each of the scanning angles. So when we actually do all this process and plot a normalized error correlation function, we show in the results that it performs much better in line of sight and non-line of sight conditions compared to the receive signal strength based method. So we just did some basic mathematical simulations on like time signals that are shifted in time, and then we added Gaussian noise with an SNR of 20 dB white Gaussian noise. And then we look at the autocorrelation coefficients for the signal 1 that's not time shifted, the signal 2 that's time shifted, a cross correlation, and then the error. So we're going to consider a normalized error in the cross correlation function for real-time data to do the detection method. So we're looking at the walkie-talkie that's placed at 90 degrees, and this is the figure for the basic RSS method. It's a receive signal strength method. So you can see that you don't get a definite peak here to say, okay, this is the actual position, or this is the actual position. When you actually look at it, the actual device was placed at 90 degrees, but when you actually measure it through the receive signal based method, you get probably a 5-degree error. It's showing up at 85 degrees. But also you get other peaks here that are prominent enough, and they're at the same level as the RSS. But when you look at the autocorrelation function, and this is the actual graph that shows the angle of arrival information, there's one peak that's prominent, and it's at 90 degrees. That is the actual position. So in this case, the error is less than or equal to the actual resolution of the array antenna itself. Let's look at another case where the non-line of sight signal is much stronger than the line of sight signal. So we have the device positioned at probably at 65 degrees, but what happens is, because of reflectors, for some reason, the RSS method measures the angle of arrival at probably 110 degrees. That's off by a lot. That is because of the reflections. So we employed the same method for the error correlation. We see that it's at the same position, 65 degrees. Now, let me tell you here that the resolution of the array antenna itself is 5 degrees. So it's within the error is within the resolution of the antenna itself. So we've seen that even in a case where the non-line of sight signal is much stronger than the line of sight signal, the error correlation function performs much better than the RSS method, which throws off by a lot, like probably 40 degrees. So we have seen that in case 1, where even though the peaks were pretty close, but there were other prominent peaks in the case of an RSS method, but the normalized error correlation function gave us a better result. And also in case of a stronger non-line of sight signal, the error correlation function performs much better. So just to summarize what we have come through the whole presentation. So RSS method fails in many occasions where there is stronger non-line of sight signal, where the non-line of sight signal is stronger, where you have multiple devices. So we have to come up with a method that's more dependent on the characteristics of the signal as such, rather than just the power of the signal. So we have come up with, in my first paper, I came up with a Hess parameter for detection. Now we have come up with a correlation method to detect multiple devices, and also to differentiate between line of sight and non-line of sight device. And there's still work to be done here, so I'm going to leave you with a future scope, the thing we're doing right now. We're doing a localization of multiple devices with a 2-dimensional array, using like 2 or 3 different methods. The RSS method, the correlation method, and the best parameter method. We look at a combination of all these methods, but to localize multiple devices using a 2-dimensional array antenna. So, thank you.
Thank you. Do you have any questions? Actually, I have a question for you. Since basically you are fusing data coming from different sources, have you considered other techniques like neural networks or other computational intelligence approaches?
No, we haven't considered the neural network approach because for training the neural network you need a lot of processing power and you need some previous data to actually train the neural network. But in our case, we are looking at methods that we can just deploy directly into the field without using much of a processing power. So in the case of a neural network, you would need models to train the neural network and previous data to train the neural network, but we want to overcome all those obstacles to come up with a new method. So that's the reason we're just going with this one.
Thank you.
Sure.
Other questions? No? Okay. Thank you again for your nice presentation. And we can move to the second paper.
We have a lot of time.